Okay, in the last module, we looked at the concept of graphs. Now we'll look at some algorithms that operate on graphs, so graph algorithms. So in the last unit, we looked at breadth-first search and depth-first search. We'll expand that today with a particular type of problem referred to as the single-source shortest path problem. And we'll look at one approach to the single-source shortest path problem referred to as Dijkstra's algorithm, named after its discoverer or inventor. So first of all, just a quick review. Graphs organize relationship between pairs of items. This is covered in discrete math classes like CSE 240, among others. Graphs typically are shown graphically with this concept of a node or vertices being connected together with edges. So formally, we can think of a graph as being a collection of these vertices and a collection of the edges. So formally, a graph G is this combination of two different concepts, vertices and edges. We usually think of the vertices as being a set, but in actual implementation, they may be implemented with a list or possibly a map or a hash set. So the concept is that each vertex is distinct. The collection of edges are usually described based on the two vertices they connect. So every edge goes from one thing into another thing. Sometimes the ordering, the concept of from and to is important. Sometimes it's not. Okay, so there are lots of different variations on graphs. So just kind of a quick review, there's the concept of a directed graph versus an undirected graph. So in a directed graph, the edges have a distinct start and end. In an undirected graph, they don't. You can kind of think of as an undirected graph as being a graph where every single edge is a two-way street. Traffic can move from either side of the edge to the other side. And in a directed graph, they have to follow the direction of the arrow. So essentially everything is a one-way street. You can convert any undirected graph into a directed graph simply by replacing every edge with two edges going in opposite directions. So something like this. Okay, graphs can be classified whether they're acyclic or not. So acyclic graphs do not have cycles in them. So this is specifically about directed graphs. So we talked about that a little bit last week. There's also the concept of whether a graph is weighted or not. So that's of particular importance to us today. And then there are, of course, combinations of these things. So last week we looked at the concept of a directed acyclic graph, or a DAG. And we looked at that particularly as kind of context for the concept of topological sort. There's also the concept of a simple graph, whether a graph is simple or not. So simple graphs are a combination of these features. They're unweighted, undirected, and there are no self-arcs. So we never have a vertex with an edge coming back to itself in a simple graph. Okay, today we will be focusing primarily on weighted graphs. So we'll focus on weighted graphs, and they may be directed or undirected. In some examples, we'll look at directed graphs. In some, we'll look at undirected graphs. Okay, so as an example of an undirected graph, last week we talked about this idea of flight distances as kind of the edge being a relation that indicates the distance between two cities. And I actually talked about the distance in terms of time. So a flight from St. Louis to Chicago may take 74 minutes, from Chicago to Detroit, 84 minutes, and so on and so forth. We could kind of think of airports as being connected together based on the amount of time a flight actually takes. So our main topic this week is the single source shortest path problem. So the concept of a path is about a sequence of edges from a start to a destination. The idea of single source is that there's one source we're interested in, so kind of a start location. So as an example, maybe we're trying to ship cargo that needs to be shipped to multiple cities, and there's some place where the cargo is produced or manufactured. So it all starts at this one central place, and we want to ship it to many, many other cities from that place. So maybe it's something like a medicine or a vaccine that needs to be delivered as soon as possible. So our goal will be to find the shortest path. So there are lots of different ways we can interpret the concept of shortest. We're going to interpret it as the sum of edge weights. So we'll minimize those total edge weights. So in our previous example, maybe it would be the minimum amount of actual time in the air to get from one city to another if we were flying amongst the cities in our previous graph. So we can also kind of think of this in terms of total travel time. Maybe it's the minimum amount of time to deliver our medicine. So this is an optimization problem, and typically it's used for the concept of minimization, although we'll briefly talk about other sorts of variants that we can easily apply this idea of single source shortest path to. Okay, We're going to try and minimize the sum of weights. So an important concept here is that we minimize the edge weights from the source to any single destination. So we'll come up with several different paths. Each of these paths is kind of the best possible path from our start to each possible destination. Weights in our graph can be many, many different things. So they could be very similar to our flight problem, where it represented the time between the individual nodes or vertices. So in this problem, we would be minimizing the overall time from the source to the destination. In reality, we're kind of minimizing the amount of time on the edges. So if we think of the edges as including things like wait time at an airport and takeoff time and all that, we're actually minimizing the total length of the trip. If we think about the edges just being the time of an individual flight and not things like layover time in the airport, then we're minimizing the amount of time in the air. Okay, but it can also be different things. It could be like physical distance between nodes. So we might want to minimize the actual amount of time, distance that we travel, which may correspond to fuel costs. So if this were shipping of ground transportation, this might minimize the total amount of gas consumed to ship things from one location to another if the edge weights represent physical distance. It could also be more clearly monetary. It could literally be cost to use a particular edge. So maybe we've got multiple ways of shipping things from one city to another. It could be over land, it could be by rail, it could be by air, and we want to minimize the total cost, and we don't really care which of those mediums we go through. So each arc could represent a different way of shipping something between two cities. So maybe to ship something from St. Louis to Chicago, it could go through the air, or it could be shipped by truck or train. So we could have three different edges that represent the costs of these three different means of transportation. Okay, the important concept here is that the single source shortest path isn't specifically about physical distance, and it really is about the concept of doing minimization of overall cost in some sense. Okay, so more formally, a path goes from vertex v0 to vk. It's considered to be an ordered set of vertices that are visited. So we can think of a path as being this collection of vertices that goes from vertex v0 to vk. But often when we're talking about paths, we're really interested in the specific edges that are being used. So we could think of this as having corresponding edges. So the first edge starts at vertex 0 and goes to vertex 1, and then vertex 1 to vertex 2, and so on and so forth. And these would have corresponding weights. So I'm going to assume we've got some sort of a function f of each vertex that gives us the weight of that vertex. So by shortest path, what we really mean is that we're minimizing this overall sum, the sum of all of the weights of the corresponding edges along the path. So this will become more concrete as we look at a specific problem. There are some related problems to single source shortest path. So one of them is all pair shortest path. So basically you could think of this as finding the single source shortest path for every single vertex in our graph, or more clearly maybe, for each individual start and destination, we will have identified a best path from one to the other. And then there's also the concept of single destination shortest path. So if we pick a particular destination of interest, we would have to find the best path from all possible start locations. Okay, those are all kind of variations on a theme, and a lot of the algorithms that we can use to solve single source shortest path can easily be used on these other two types of problems with some modifications.